Welcome back. In the first few videos, I drew conventional initiating device circuits and I would connect heat detectors to them. And I asked you to imagine that a heat detector was just a switch that would close. It was a normally open device whose switch would close. So if you look on the left, on the back view of this diagram, I drew it like this, with a little armature that would close when the device went into alarm. And I said that that wasn't exactly how it worked, but it was a fairly accurate way to think of it, because when a heat detector goes into alarm, it's basically two pieces of metal closing, shorting together. So a switch was good enough to imagine or to explain how a zone works, a conventional zone works. So we'll wire this up real quickly. This is again the back view. So the yellow is one of the screw terminals, the orange is the other screw terminals. We're going to wire it to a fire alarm panel, but we're not going to spend a lot of time on it because we've already done this a bunch of times at this point. So we got positive on one side, negative to the other. Assuming this is either the last or the only device on the circuit, we'll just put the resistor here. So now all the panel sees is a resistor. Okay, so that's how you'd wire it up, and that's what it would look like from the back. This white thing here is a picture of a heat detector. It's a pretty common type. There's a bunch of different types, but it's a pretty common type of heat detector. And right now we're discussing how a fixed temperature heat detector works. So if you go over to the left here, there's kind of a lot going on. Again, this is the side view over here on the right. So the yellow is one screw terminal, the orange is the other screw terminal. And let's look at what they're connected to. So the yellow one's connected to a piece of metal here, which is connected to a spring. And that spring is pushing down on this metal plunger switch. And the plunger switch is not touching this orange ring around, the ring that's around the plunger switch is only touching the other contact. So if we were to say we were to hook this up to a panel like it is on the left and follow if any current can flow, one side of the circuit would be going through all this metal, through the spring and to the plunger, but it's not touching the orange. The orange is, hopefully you can see by the drawing that I tried to make it clear that that was not actually touching the other contact. So all that's touching is down here, this plunger, which would not be, it's not touching the other side of the circuit. It's not, that would not be a conductor. So that's just a little plug. The pink thing on the bottom there is like a little plug. So the pink thing is connected to this disc down here, and it's connected to it with this fusible alloy. And an alloy is just a combination of different types of metals, basically. But this alloy has a property that it will melt at a certain temperature. So there's a few different types of fixed temperature heat detectors. The most common is one that uses an alloy that melts at 135 degrees Fahrenheit. And then the next most common, you'll see sometimes in kitchens and stuff like that, is at 195 degrees. And there's charts on what the ambient temperature should be in the room when you use each one. Like, I believe it shouldn't be over 100 degrees when you're using a 135 degree heat detector and so on. But you'd look that up for each application. But just to get the idea of how it works. So if this were to heat up, there's a little heat collector here. So it's basically a metal ring on the bottom that would heat up, and when that got to a certain temperature, that alloy would begin to melt. Once that alloy melts, this plug is no longer going to be held in place. So this spring is pushing force down onto that plug. Once this alloy melts, it's going to allow this plunger switch to connect with the orange ring, which is connected to the other terminal, and essentially these two are going to be shorted together. So that's what's going to cause your increase in current. It's going to be essentially going right through there, and it's going to put your zone in alarm. So that's how the most common type of fixed temperature heat detector works. The next type is what's called a rate of rise heat detector. And you can see the title at the top here, I put rate of rise and fixed temp, and I'm going to explain that in a minute, but let's focus on the rate of rise. So on the left I drew the panel again, but we're not going to go through the trouble of wiring it up. You wire it up exactly the same way. I use the same picture because from the outside they look basically the same. There'd be some labeling on the outside that would explain that, that would say it's a rate of rise or it's a fixed temp or whatever it is, but they basically look the same. So if you look internally on this rate of rise, the way this thing works, focus on the top part up here right now. Don't focus on the spring on the bottom and all that stuff. So you have the two contacts again that are pretty close together, and they're surrounded by this flexible diaphragm. And what happens is, if if the air temperature were to heat up around this device, the air inside this chamber here would heat up, and that, when air heats up, it expands. So it would be pushing on this diaphragm, and so the air is kind of pushing in every direction, but it's pushing on this diaphragm, which would cause these to short out. And usually, rate of rise heat detectors go into alarm when there's an increase in temperature of at least 15 degrees Fahrenheit per minute, and that's just the properties of the metal, that how quickly they bend. And what happens is if it were to slowly increase, there's a little air vent in this detector, and so the air is going to be surrounding the heat detector, but some will be getting out through the air vent. And so if the temperature increases faster than it can escape through this air vent, that's what's going to contract this diaphragm and push it up on the contacts and short it. Now, most rate of rise heat detectors are combined with a fixed temperature device as well, and that's what's on the bottom here. So this works kind of similar to the last one. There's this this would be kind of your switch. I guess this is brown plug down here is your switch, and there's a spring that's now forcing this switch up. And I called it solder here, but it's that alloy. Solder is essentially the same thing, which would melt at a given temperature. If it's 135 degrees, that's what's holding this in place right now. As soon as that melts along the bottom, the spring is going to push this plug up. It's going to hit this diaphragm. It's going to push the two contacts together, and that's what's going to cause your alarm. Those are the two most common types of heat detectors you'll see, and it just depends on what area you're using them in and what application you want. The next kind is called a rate compensation, a rate compensation heat detector. And what that means, well, let me explain what thermal lag means, because in the first heat detector that we use, there's something called thermal lag, and that is the amount of time that it takes a heat detector to go into alarm once the air temperature reaches the alarm temperature. So in other words, if the air in a room were 135 degrees, it would take, the heat detector is not going to go into alarm the second that the air reaches that temperature, because it takes a while for the heat collector to warm up. It takes a while for the metal to actually warm up to that temperature, and so on. So to help compensate for that, there's this other type of fixed temperature heat detector called a rate compensation device. The way this thing works is there's these two inner expansion struts, which I labeled, and these will expand at a certain temperature. So say this one's rated for 135 degrees. When it gets to 135 degrees, this is going to expand, and these two contacts are going to touch. But if there's a rapid increase in temperature, this outer shell, this would be like a metal tube that this whole thing is surrounded in, this outer shell will also expand as temperature increases. So if there's a very fast increase in temperature, even before that temperature can penetrate the shell and stretch out these struts, this shell will expand this way, pulling these together, and the expansion struts would still be expanding as well and coming together, but the outer shell would be pulling on it, which is going to stretch these out even sooner, and it's going to allow these two to shut. And that's kind of that's how it compensates for thermal lag. Now, the last type is more common in addressable heat detectors, which we haven't talked about yet, and that is a thermistor. And a thermistor is basically, it's like a resistor whose resistance changes with heat. So if something heats up, the internal resistance, the resistance of that device will change. And so then there's onboard circuitry that will process that, electrically, and it'll process that change in resistance, and communicate with a panel and let it know when there's alarm, when there's not. A lot of times you'll see, this is kind of an example of a heat detector, and the thermistor would be kind of right in the center there. But these are most common with addressable devices, but you'll also see them on some conventional heats, and more commonly on smoke detectors that employ a heat detector as well. So there'll be a little thermistor on a smoke detector, and then it's a combination device to detect both smoke and heat, and you'll see that as well. I think that's where I'm going to stop this one, and I'll see you in the next video.